ladies and gentlemen. This presentation concerns the main design principles of ground improvement that we have redacted within the framework of the second generation of the Eurocode. First of all, we can question the scope of this chapter, because with ground improvement we do not create a geotechnical structure in itself, but we allow to build on soft soil, generally presenting very poor mechanical characteristics, and thus the design of the structure supported by the soil which has been improved has to be designed according to another clauses of the Eurocode 7 part 3. Thus, we have to consider the improvement of the soil properties, but the design of the geotechnical structure in itself, relying on this ground improvement, is to be performed according to another clause. We have two possibilities, actually, to reinforce, to improve the soil properties. We can directly improve the soil properties in itself without addition of non-rigid on rigid inclusions, and in this case we model the improved ground with conventional ground model, but taking into account the fact that the soil properties have been improved by our execution process. We have another possibility, it's to install rigid or non-rigid inclusions into the soil, into the soft soil, and in this case we have to consider the overall performance, taking into account the resistance of these inclusions and the resistance of the soft soil. At the beginning of the process of redacting this new chapter, this is a baby chapter, in fact, this is the first time that we deal with ground improvement in the Eurocode. It was very challenging because ground improvement, we use a lot of different execution techniques, presenting a versatility in terms of nature of the technique that we are using. We have compaction methods, we have consolidation methods with vertical drains, surcharge, we have grouting methods with the use of mixture, water, cement, with specific resin sometimes. We have the thermal methods, and we can also add inclusions into the soft soils with different nature of inclusions. Up to now, we had only classification of ground improvement based on execution techniques, based, for example, on the work of the ISSMG TC211, with a classification considering the nature of the way the soil is improved. And for the best of my knowledge, this is the first time that we have a classification of ground improvement based on the way the design will be done. And that's a good thing, I believe. Thus, I'm going to explain that in more detail in a few slides, but basically we have the following class of design for ground improvement, taking into account the diffuse or discrete improvement on the soil, and the fact that we can or not measure an unconfined compressive strength for the ground improvement material. And thus, depending on the case, and that's a little bit challenging for the people of practice, one execution technique can fall in different design class. First of all, we have the class A1. We have a global soft soil, a global zone of soft soil, which is improved without addition of inclusions. This is typically performed with dynamic compaction, with the use of enhanced rollers, or with the use of vertical drains combined with surcharge, for example. But at the end, you have no possibility to obtain a UCS for the ground improvement. Afterwards, we have another class of ground improvement, class A2. We perform a global mass stabilization, for example, but at the end of the process, in this case, we can define a UCS for the improved soil. That's an example of a field followed a few years ago with Adrian in the polders in the Netherlands, in the region of Gouda. If I correctly remember, we have 5 meters of PT soil, and this PT soil was treated with a global mass stabilization process, mixing the PT soil with an hydraulic binder, and at the end of the process, after hardening of the soil cement or soil lime mixture, we can define a UCS value for this global mass, which has been stabilized. Afterwards, we have the class B1, the discrete with non-rigid inclusions. This is typically stone columns, such as used in practice. And last but not least, we have the B2 class with discrete improvements on the soft soil with rigid inclusions, which can be cylindrical, for example, with the CMC process, or which can be cylindrical or rectangular with the use of different boring tools, such as for the CSN cutter soil mixing method here. Thus, this is the basic of this ground improvement chapter, the use of different class for the design of ground improvement. Another important concept is the differentiation between pile and rigid inclusions. It looks indeed like a pile, but it's not a pile. First, you see that the concept is based on the absence of structural connection between the top of the rigid inclusions and the supported embankment or sprit foundation by the way of a load transfer platform or without load transfer platform, because LTP is not mandatory to have ground improvement, but what is important is the absence of structural connection between the top of the rigid inclusions and the supported sprit foundations. But in the absence of a LTP, a single pile used with a ULS cannot be designed as a rigid inclusions. We cannot disguise a rigid inclusion. We cannot disguise a pile in a rigid inclusions. Thus, for ULS, a single rigid inclusion is a pile, and you have to design that according to the clause 6 presented this morning. For an use in settlement reduction, you can use these single rigid inclusions according to this clause 12. Another challenging discussion was the integration of the geometrical properties in the chapter 12, because when you are working with soil mixing or with jet grouting, you know that execution tolerances play a large role in what you obtain at the end of the process of execution. And thus, a compromise was found inside this clause 12 to refer to the relevant execution standard for what concerned the acceptable deviations of the geometrical properties. You have a list given taking into account the execution process that you use, given in the Annex I of the third part of this Eurocode 7. If you have nothing in the execution standard, you can rely on the National Annex, and in absence of information in the National Annex, you can use the requirements of the relevant authority for your project. What is important to mention is a sentence of the first Eurocode. This is the fact that for verification of limit states using the partial factor method, the deviation of a geometrical property that is within this specified tolerance is assumed to be catered for by the partial factors for the force, material, etc. Another discussion concerned the definition of the ground investigation for ground improvement, and it was based, such as for the other clauses, on the concept of zone of influence, with a minimum depth and horizontal extent for this ground investigation to be defined, to be sure that you have enough information inside this zone of influence. This is done taking into account the nature of the ground improvement process, diffused or discrete. Because for diffused ground improvement, you perform the ground investigation until 5 meters under the soft soil which has been improved here. And for the discrete one, you can see that you perform the ground investigation 5 meters below the base of the rigid inclusions, or 3 times the diameter of these rigid inclusions. But do not forget the engineering judgment and the analysis of the data that you have with ground conditions, what you expect with your local ground conditions, and thus you can increase or decrease these informations taking into account what you are expecting on site. Another challenging topic of this chapter 12 was the definition of the material properties. For the soft soil, which is just improved but staying as soil, we can rely on the different clauses of the second part of Eurocode 7. For the different inclusions made of concrete, steel and timber, we have other structural Eurocodes. But this is more challenging to determine a representative and design value for such kind of material, soil mix or jet growing material. In this case, we base our design approach on the consideration of the phase of the project. Thus, before execution, you have no material to be tested, and thus you assume your nominal value based on a cautious estimate, and this cautious estimate is based on the comparable experience, and most of the time in Europa, the comparable experience accrued by the deep mixing or jet growing contractor. But after execution, you shall verify that you encounter this resistance on site by testing. That's very important. Thus, how is the representative value computed according to this approach? Thus, based first of all on a characteristic value if you have at least n samples, and this n can be adapted in the National Annex, depending on the way you do the computation. But thus, you have your characteristic value here, and you have to factorize this characteristic value by two conversion factors. The first one, accounting for long-term effects, such as for concrete material here, and eta C is equal to 0.85 for geotechnical structures. We said in the past permanent structures, and is equal to 1 for temporary structures. Thus, afterwards, you have also this eta T factor accounting for the difference in time between the testing, typically 4 weeks after execution, and when the class 2 ground improvement material is exposed to the design stress on the field. For this eta T, the value of this eta T should be based on testing, because it is also possible to have higher value than 1 for this eta T. The resistance can increase beyond 4 weeks. And almost in Europa, we are using CEM3-based cementitious material or hydraulic binder with a long-term increase of the strength. But it should be based, this value of eta T, on testing this. At 4 weeks, this is 1. And as you can see here, we give a tool, a graph in the annex of Eurocode 7 part 3 to determine or to approach the value of eta T, taking into account the type of cementitious material that you are using for the stabilization. At the end, you have to determine the characteristic value of the data set that you have, and this is equal to the P fractile of the data set. And most of the time for soil mixing, jet growing materials, you use a log normal distribution, except when you are in the practice with subpopulation in your data set. In that case, you can always use a cumulative frequency curve to determine the P fractile of the dataset. I will give an example later. Now, we have fewer than 1 samples to be tested, and in practice that arises a lot. You have a few number of samples, and in this case you have to compute the representative value based on a nominal value. And this nominal value is taken as the minimum of the following values. The minimum value of the results of all your data sets, an arithmetic average value factorized by K, which is typically 0.7 in Dutch and Belgian practice. In Germany, this is close to 0.7 also with the DIN standard, and a maximum value of 12 MPa, which comes from Germany also. And before execution, you have no data, thus you use a cautious estimate, and this cautious estimate is taken as the nominal value. But you have to factorize it by the two aforementioned factors, the conversion factors. And thus you have your representative value. You have to obtain the design value, and thus you factorize your representative value by a partial material factor, which is taken from the Eurocodes for concrete, steel and timber, and for soil mix and jet growing materials, you can take 1.5 as partial material factor, and you use that independently on the material factor or resistance factor approach that you use, because we do not allow a structural failure of the ground improvement material in such kind of design. Thus, for the design verification of taking into account the design stress that you encounter in the design. If there is no relevant other Eurocodes, for example Eurocode 2 for concrete, it is possible to use the following approach. The ULS may be verified, demonstrating that the design effect of actions do not exceed the failure envelope that you see here. But this is if you are using an explicit calculation of the principal stress in your design approach. If you have a separate computation of the shear stress and the compressive stress, you have to apply this range of simplified stress verifications with an extra factor of 0.7 on the design value that you just compute. And for the shear stress, it is taken equal to 0.2 times the design value of the UCS. Testing. Material control tests. You shall verify that you encounter the values that you use in the design. But for the other types of testing, it is not mandatory. First of all, you have to adapt the types of test or monitoring to the nature of the execution technique. Because as you see, we have a lot of different execution technique, and we have to use a methodology of monitoring of testing suited for this execution technique, and you can refer to the different execution standards for that. Some tests may be done, this is not mandatory, before the execution, but what is mandatory, this is the verification of the resistance of the ground improvement material, because you have to verify that the resistance, the strength that you use in the design is really encountered in practice. And thus you do that with a minimum number of control tests, which should be determined based on local practice. Because everywhere in Europe, we are not using deep mixing or jet grouting for similar kind of structures. And thus in this case, we give a minimum of the minimum number of tests that you shall perform to verify that you encounter the resistance that you assume in the design. About the material control test, you have extra information given in the code, but only recommendation and permission. For example, taking into account the dimensions of the samples that you test. This is a current practice to test 8 to diameter ratio of 2 for concrete before soil mixing, for example, to have more tests to be interpreted, taking into account the variability of the material. For example, we commonly use a ratio of 1 in a lot of different countries. And thus, you may apply a 0.8 if you want, adapted to your national practice, because that takes also the other factor, the N samples, the other factorization factor of 0.7 that you have in the code. Thus, you may apply that, but that's not mandatory. Another remark, after conducting all the UCS tests on suitable samples for testing, the results of the test specimen with unmixed soft soil inclusion larger than 1/6 of the diameter can be excluded from the analysis. And this is based on the fact that these inclusions will have a large influence on the results of the test on a small sample, but similar unmixed soft soil inclusion in a soil mix or jet grout element on site will have neglecting influence. And you can do that until a limit of 15% of all the UCS results that you have in your dataset. And based on the results, you apply the process that I present today to determine the characteristic and the design value of UCS. Small example, we are here in Belgium with a project of soil mixing, performed according to the execution standard, project of rigid inclusions, lifetime of 15 years. Thus we have a permanent project, a geotechnical structure thus, and we are working in clay with ET layers in this clay. We have cored 41 core samples, and the testing is at 4 weeks. We have this histogram. This is a logarithmic representation of the results. There are discussions with the customer about the perfect shape of this log normal distribution, and thus for this exercise we are using the cumulative frequency curve to avoid longer discussion with the customer. we take the 10% fractile of all the results, and we obtain a 1.8 MPa, which is too low for this project. Why? Because we have to consider the presence of 5 test specimens in the data set with large unmixed soft soil inclusions due, for example, to the presence of this peaty soil. If we are excluding these results, and this is allowed, we obtain a higher value, which is correct now, more representative of the practice of the real material that you perform on site. Afterwards, you factorize this value, characteristic value, by the true conversion factor, and you obtain your representative value. Eta T is equal to 1, testing at 4 weeks, and for a high lifetime, you have your conversion factor here to be applied. With the partial material factor, you obtain at the end of the exercise the design value of the UCS. And this result is based on a statistical analysis because you have a lot of results. But most of the time you are not lucky and you have less than 10 samples, for example. And in this case, for the exercise, I take the 9 small values of the data set, and we have to use a nominal value this time, and no more the characteristic value, because we have less than 10 samples in this case. And thus in this case, the minimum is the minimum of the 3 following values, as I explained it, and for us, this is the arithmetic average value factorized by the 0.7, which is relevant. We integrate that in the formula to obtain the representative value, and at the end, we have this design value, which is obtained. And as you can compare, this is a lower value than what you have with a full statistical analysis. We do that exercise for more than 50 fields. We all construction sites, and we have always the same results. The more samples you have, the less the extra safety that you have to apply in the computation. Because the more you know, the further you go in the design. That's very important, and that is in line with the philosophy of the Eurocode 7, I believe. Thank you very much for your attention, and I let the floor to my colleagues to speak about non-rigid and rigid inclusion stuff.